All right, everybody. So here's angled projectiles. Okay. So this is, dang, you all might not even know what this game is anymore. Now I feel a little old, but Angry Birds is a great example of angled projectiles where the physics actually is similar to what we'd see in a situation that has no air resistance, things like that. So we've been looking so far at just, okay, we launch something horizontally, then it goes down. But what if we don't launch it horizontally? What if we launch it up? Or what if we launch it down? Anything like that. So this is where we get to look at the actual motion of when we throw something, right? Because almost never is something thrown flat. So now we're going to actually look at this motion here. Okay, so angled projectiles. I want to do a quick triangle recap. Again, this is just triangle math. This entire page, this slide is everything that we will use for triangle math this year. It's everything. So we just need sine, cosine, and tangent. So I have this triangle set up here for you on this top right corner with an A, B, and C. I just labeled them just like we would do for Pythagorean theorem. So a squared plus b squared equals c squared. You will definitely need that. And then you have sines, cosine, and tangent is where if you're given only one of these in the angle, and it can be this one, it can be B, it could be A, it could be C, but if we're given only one of the sides and the angle, we can use any of these identities to figure out the other sides. Or if we're given just multiple sides but we're not given the angle, we can figure out what the angle is using this inverse sign. Right, that's a button on your calculator. If you just hit second sign, that should give you the inverse sign. And then you just take the fraction b over c or the fraction a over c, whatever function you're using, whatever you have against whatever angle you're interested in. All right, and then the SOHCAHTOA sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. I hope you all know that by now, but this is a quick recap. This slide is everything we need for triangles for AP Physics 1. All right, so angled projectiles. So we've done these horizontally launched objects, but now we're looking at the ones that are not launched horizontally. Here's what we're going to do. We're going to treat it as two horizontal projectiles. So everything that we've done for the last couple of class periods, we're just going to treat it as one on the way up and then one on the way down. So on the way up, I'll get these out of the way. On the way up, and this is why we come back to the triangle math, right? Because this will be our overall, like, let's say this is our initial velocity that we're launching it above ground. Then this side, this would be our velocity initial in the y-axis. This side would be our velocity initial in the x-axis, which, as a reminder, initial doesn't really matter, so it's really just x-axis, because right in the x-axis there's no acceleration. So this is where we look at these, I'll call it the velocity triangles, where we take the v overall, we take the velocity in the y-axis and the velocity in the x-axis, and we use these triangles here. So on the way up, we start with a velocity initial. We start with the velocity initial, which means we can break that down into our components of velocity initial in the y and our velocity in the x there. But then when we finish, our velocity is completely horizontal. So this would just be v final. However, it's, oh, hi Tango. Cat's making an appearance. When we finish, it is just completely horizontal. It is v final, but it's just sideways there. So v final actually is just equal to Vx because it's horizontal. However, that also means that, because right here, is it going up and down at all? It's not. For just one single instant, our object is not moving up or down. It's just moving straight sideways, which means that at this instant, velocity in the y-axis is 0. So for the first half of the motion, that means that velocity final y is equal to 0. That's for the first half of the motion on the way up. And then for the second half of the motion, I'll get a different color to separate this all. Right, it starts completely horizontal. That's our v initial, but that's truly just vx. But there it's horizontal, so velocity initial in the y-axis is equal to 0. But then as we move along, as gravity pulls it down, our velocity in the y-axis is slowly increasing. So it ends, here's our overall final velocity, so v final. We have a vertical component to that, v final in the y-axis, and a horizontal component to that, v final in the x-axis. But once again, it's really just v in the x-axis. So I'll make it look nicer there. So it's just velocity in the x-axis. All right. So we don't have enough information to solve the problem unless we split it into two like this. Unless we use this point of velocity in the y-axis is equal to 0 at the top. Because otherwise there's too many unknowns and there's not enough givens. Okay. So let's look at this. Time. Time is always the most important thing. This is just like horizontal projectiles. Because, right, we're just treating, it's two horizontal projectiles problems, just in one. That's all this is it's just two problems in one. So we have to figure out time because that's the only way we can go between the y-axis and the x-axis. All right, so time up and time down equations. These are on your equation sheet. The AP test does not give them to you. However, I do want you to use them. They are very helpful to you, and I hate to say this word, but memorize the time up and time down equations for the AP test. I hate that word. It's an ugly word. Memorize. A shiver. However, it's just more helpful for you if you memorize those couple of equations. I'll show you how to derive them right now. So time up. Time up. All right, so we start with our velocity triangle here. We start with v initial. That has a v in the x component. It has a v initial in the y component. What we can do, though, is because v final y is equal to 0, right? It's not moving up or down at all at that instant. V final y is equal to 0 for this first half of the motion. So we can say, let's take that v initial in the y-axis. We also know that this is on Earth, so acceleration is 10 meters per second squared down. 10 meters per second squared down. So let's take this equation, v final equals v initial plus at. All right, so we got v final, well, that's 0 is equal to v initial. We don't know that, but we're going to say this is all in the y-axis. So this is all in the y-axis. Plus, and then it's 10 meters per second squared down, so we'll do negative 10 times time. Okay, so we need to figure out time. So this is just for the half that's up. So I'm going to add 10t to both sides. So we've got 10t. Actually, I'm going to go through. I'm not going to put in 10 here. I'm just going to use the letter g. You can use the letter g. So acceleration is equal to g, but it's negative g really, and g is 10. It's that 9.81. However, it just makes it easier to represent in an equation. So I'm going to add gt to both sides, so that gets rid of this term there. So gt is equal to v initial in the y-axis. So our time on the way up is equal to v naught y over g. All right. Time up is equal to v naught y over g. Great. That is a simple equation. We like simple. Okay. Now let's do time down. So time down looks at it from another perspective. Time down is v initial in the y-axis here is now 0 meters per second because we're looking at the second half of the motion. We also have acceleration is negative g. We're also looking for t here. And I'm going to use the fact that this is the maximum height it goes. I'm going to call this h max, just the maximum height that it ever does. So we're going to use the equation h is equal to v naught t plus 1/2 at squared. We're going to use that equation there. Now remember, h and d are interchangeable anytime we're using these equations. Okay, so v initial, right, this is on the y-axis. So y-axis. V initial here is now equal to 0. So that actually just goes away because v naught is equal to 0. So we've got the distance it travels, so h max is equal to 1/2 g t squared. Now truly this is negative h max and negative g because it goes from the top down, so negative h max. And then g is pointing down, so it's negative g. But since there's a negative on both sides, we can get rid of that. All right, I'm going to multiply both sides by 2 to get rid of this 2. Okay, so 2h max is equal to gt squared. Okay, I'm going to bring this down over here. Okay, now since we're looking for time, right, this is our time down. I'm going to divide by g, so 2h max over g is equal to t squared. And since we just want t, we'll do our time down is equal to square root of 2 times our maximum height divided by g. All right. There's our time down equation. So these two that are boxed here, you don't need to know how to derive them, but I did want to show you that they come from motion equations. They just come from motion equations. I'm setting up these individual places, or these individual variables in these situations for, in this red here, the time on the way up, where v final y is equal to 0. And then in the green here, the time on the way down, where v initial y is equal to 0. So this shows us how we can separate out angled projectiles into the first half of the motion and the second half of the motion. All right. So just like horizontal projectiles, we'll treat the axes separately, which you might have noticed that I've done. Time only depends on the y-axis. So this is a great note to see here, that our time up equal to v naught y over g, and time down, I'll do this in the other font or in the other color, our time down is equal to square root of 2 h max over g. Notice how v naught y, g, acceleration of gravity again, and h max, those are all just in the vertical axis. So that's all that time depends on. Distance traveled in the x-axis, right, that only depends on how long it's in the air and its x velocity. Because velocity in the x-axis, right, this is just the definition, is displacement over time. So our displacement in the x-axis, but that's just what we use the variable d for, is x-axis. Y-axis is h for height. So d is vx times time. So you get the time from the y-axis, and then you can plug it into the x-axis to find the distance traveled. All right. Halfway through. Okay, example problem. A human is shot out of a cannon at a circus. If the human cannonball reaches a maximum height of 6.3 meters and lands 15.8 meters away from the cannon, A, how long was he in the air? And B, how fast was he shot out of the cannon? Okay, A, how long was he in the air? All right, so this is actually where we get to look at a cool thing between the time up and the time down. Between this time up and time down, I'm going to back up just a little bit here. What happens is when we have an angled projectile, if we start and end at the same height, it actually is going to take the same time up as it will the time down. So just starting and ending at the same height means that time up equals time down. So what that means is our time total in the air is either 2 times our time up, wrote terribly. It's either 2 times our time up or 2 times our time down. And we just get to pick, okay, are we given initial velocity in the y-axis or are we given its maximum height? Okay, so now let's go back to our problem over here. Okay, so how long was he in the air? Well, I'm reading through. We're given maximum height of 6.3 meters and lands 15.8 meters away. Okay, so how long was he in the air? Well, we're given maximum height, so let's use the fact that the time total for something is equal to 2 times. And which of our time equations uses maximum height? Well, it is time down. So it's 2 times square root of 2 times our maximum height over g. Right, this is our equation part of the guess method. I just wrote the equation there. Okay, so this is 2 times the square root of 2 times 6.3 divided by 10. All right. So if we get the calculator app, search here, type to search. Okay, I need my calculator. Oh, calculator's right there. Yes, calculator. All right, so we need 2 times the square root of, oh, heck, I forget how to do all these in here. Okay, so I think we need to do the inside 2 times, not 0. Sorry, bear with me here. 2 times 6.3 divided by 10 equals, okay, 1.26. That's what's inside the square root. So let's take the square root of all that. Okay, so we've got 1.122, and that gets multiplied by 2. Okay, so this gives us, oh, that went away too fast, 2.24, and this is a time, so it's seconds. All right, 2.24 seconds. Okay, and then part B, how fast was he shot out of the cannon? So now this is using an interesting, not necessarily the most interesting, but one that we've already learned. This is going to be our velocity triangles. Because if it's asking for how fast, that means we are looking for v initial. That's our unknown in this situation. But to find v initial, we have to just be able to do, right, it's this little right triangle here, so we need v initial y and we need v x. Okay, and then we can just do the a squared plus b squared equals c squared. Okay, so we're going to have to use 2 different things here. We're going to need to figure out v naught y, and we're going to have to figure out velocity in the x direction. Okay, let's start with y, because that's what we've been working with so far. Well, we got that our time up is equal to 2.24 seconds. So let's say here's our given time up, 2.24 seconds. Now remember that's equal to time down. That's our time total. My apologies. That is our time total. So ignore that so far. Time total is equal to 2.24 seconds, which means our time up or our time down either way will be 1.12 seconds. Okay, and we're also, this is the y-axis, so we know acceleration in the y-axis is negative 10 meters per second squared. All right, and we're looking for velocity initial in the y-axis. So there actually, we can use the time up equation is equal to v naught y over g, right? Because g, that is our acceleration here. That is the acceleration there. So we can set this equal to, or just I'll multiply g on both sides. So g times time up is v naught y. So that's going to be equal to 10 times 1.12. So v naught in the y-axis is 11.2. It's the velocity, so meters per second. All right, there's one of our velocities here. Okay, So now let's go to the other one. So we got v naught y. Great. Now we need to get v in the x-axis. Well, what's the definition of velocity? Velocity is displacement over time. We have our displacement. It tells us it's 15.8 meters. We have the amount of time that it took to go the entire path of the cannon. We know how much time that was. That was 2.24 seconds. All right, so 15.8. Let's clear this out. 15.8 divided by 2.24. That gives us 7.05. 7.05 meters per second. All right, so there's our velocity in the x-axis. Great. So now we know v naught y. We know velocity in the x-axis. We can just use a squared plus b squared equals c squared. So velocity, it won't let me write below. Okay, I'll have to write a little bit smaller here. Okay, so velocity in the x-axis squared plus v naught y squared equals just our initial velocity squared, because that's what we're looking for, is how fast was he shot out of the cannon. We're looking for this initial velocity overall. So this will be our overall velocity square root of 7.05 squared plus 11.2 squared. Now let's figure out that. Okay, so let's clear this out. 7.05 squared plus 11.2 squared equals, okay, so there's the sum and take the square root of that, 13.2 velocity, so meters per second. All right, there's our example problem. Okay, if you need to go back and rewatch this, re-understand it, or just pause the video and take a look at it now, please do so before you get too lost on the next ones. I'm going to take the next ones a little bit faster, though. Okay, let's say a quarterback throws a ball 42 yards down the field, and if it was thrown at 20 meters per second at an angle of 37 degrees above the ground, how long was it in the air? All right. First thing we're going to do, this is 42 yards. I don't like yards because we're in physics. So let's convert to meters. So 42 yards. If we multiply by 3, that gives us our feet. And it's 3.28 feet per meter. So 38.4 meters. Okay, 38.4 meters. Great. Okay, if it was thrown at 20 meters per second at an angle of 37 degrees above the ground. Okay, this is pretty much what we're going to have to do. So this is our velocity initial. It tells us was 20 meters per second. This angle here is 37 degrees. Pretty much we're going to have to draw a velocity triangle almost every single time we do one of these problems. Every single time. Okay, so we're looking for how long was it in the air. So that is time. So we need to find our time total, which is equal to, right? It's 2 times either time up or 2 times time down. So this means we need to find either its initial y velocity or its maximum height. Well, we're given some stuff to do the velocity triangle, so let's find y velocity initial. So we can do this with our triangle math. We want v not y, so that is opposite, and we have the hypotenuse, so we can use the sine of 37 degrees is equal to v naught y over v naught. Now you can either plug this into your calculator, right, because v naught is 20. You can either plug it into your calculator and figure out, okay, v naught y is 20 times the sine of 37 degrees. Make sure you're in degrees mode. Or here's why I like giving 37 degrees. Because 37 degrees, and I'll do it in a different color up top. 37 degrees, that is actually a 3, 4, 5 right triangle. That's one of our right triangle families. So that means that the other angle is 53 degrees. So I'll give a lot of 37 and 53 degrees. This is just what we scale them by. So if this side over here, if our hypotenuse is 20, that means V naught y must be scaled by the same factor of 3, so V naught y has to equal 12. So we would have 12, our velocity in the x-axis would be 16 because this is equal to 20. All right, so 12 meters per second. If you have trouble with that, we'll practice it all the time. We will do a lot with it. So don't worry, you can just plug this into your calculator like this and it spits out exactly the same answer. It might be like 12.001 or something like that, but basically the same. Okay, so we have our V initial y, so now we just need to find our time total is equal to 2 times our time up, so 2 times V naught y over g. Okay, so our time that it's in the air, 2 times 12 meters per second divided by 10. So that turns into 2 times 1.2, 2.4. This is time, so seconds. All right. So that one was actually a little bit more simple. That was a little more simple. We didn't even need to use the fact that it was 42 yards down the field. We didn't need to use that, which is kind of cool. All right, let's go to the next one. On the next play, the quarterback throws the ball 53 yards down the field. Oh, 53 yards. We're going to have to convert that to meters probably. So 53 yards right, times 3. This puts it in feet over 3.28. This is in meters. Okay, 48.5. 48.5 meters. By the way, this process is one I do every single time. If I see a unit I don't like, I will almost always just automatically convert it to the unit that we do like. Okay, so it reached a maximum height of 18 meters. How long was it in the air? All right, well, I tell you maximum height, and now we're looking for how long, so we're looking for time. All right, well, time total, remember this is 2 times time up or 2 times time down. Well, time down, let's use that one, time down, because that's equal to 2, or time down is equal to square root of 2 times our maximum height divided by g. So if we plug all this in, this just gets us 2 times the square root of 2 times 18 over 10. All right, so this is 2 times the square root. 2 times 18 is 36 divided by 10 of 3.6. Okay, so the square root of 3.6 is this. We need to do times 2. Gives us 3.79. All right, so 3.79 seconds. All right, well, that was pretty fast. Great. If you need to pause the video and go back and rework this yourself, feel free to do so. Okay. Oh, by the way, where it says 1 decimal place is because this used to be, I used to have it on a different platform where you actually submitted the answers, but we'll keep it to 3 sig figs, so ignore that. On a similar note, ignore that, ignore that, ignore that. All right. Basketball player shoots from a 3-point line, and the ball stays in the air for 1.68 seconds. Basketball hoop is 10 feet off the ground, and the player made a jump shot, releasing the ball from 10 feet also. Okay, what I like about that is that it starts and ends at 10 feet, so it starts and ends in the same place. That means that time up is equal to time down. That's what's helpful to us. Okay. So it's in the air for 1.68 seconds. How high did it go above the ground at maximum? Well, we can say time down is equal to the square root of 2h max over g. If it's in the air for 1.68 seconds, that means that time down is half that. So 1.68 divided by 2.84. So 0.84 seconds is equal to the square root of 2h max over g is 10. All right, I'm going to pull out my actual calculator just so I don't have to continue doing this. I'll square both sides, so 0.84 squared. Okay, and then times 10 divided by 2. This tells us that our H max is equal to 3.53. Goodness sakes, 3.53 meters. All right, now remember that is plus the 10 feet. So plus the 10 feet. So if we convert 10 feet into meters, divided by 3.28, this means that our actual maximum height, if we add those together, so 10 feet into meters is 3.05. So 3.05 meters plus 3.4 or 3.05, sorry, 3.53 meters. This gives us 6.58 meters. 6.58 meters, that's our maximum height. All right, what is its initial velocity? Okay, so we're going to have to do the similar thing that we did earlier, figure out what is v naught y and what is vx, and use our Pythagorean theorem here. Okay, anytime it asks for what's its initial velocity, we're going to have to do that the whole time. Okay, so v naught y, we'll use the fact that time up is equal to v naught y over g. So we can do 0.84 seconds is equal to v naught y over 10. So v naught y, our initial velocity in the y-axis is 8.4 meters per second. Okay, now we just need velocity in the x-axis. Well, it travels 23 feet 9 inches. I'll save you the pain here of converting from feet to meters. That is 7.24 meters is that horizontal side. So that means velocity in the x-axis, well, it traveled 7.24 meters in 1.68 seconds. So 7.24 divided by 1.68. That tells us that our velocity in the x-axis was 4.31 meters per second. Okay, so we have this. Now we just need to plug it into our a squared plus b squared equals c squared. So 8.4 squared and 4.31 squared. Add those together, take the square root. This spits out our velocity initial is equal to 9.44 meters per second. All right, there's that. Okay, finally, at what angle was the ball released? Okay, well, we have our triangle again. Let's take our initial velocity. We're looking at this angle here. It's always the angle either above or below the horizontal. Just depends on whether it's up or down. Okay, so this one, v naught y, this is 8.4 meters per second. This one at the bottom, this is 4.31. So 4.31. We can take the inverse tangent, right? Because tangent of theta is going to be equal to our opposite over adjacent, 8.4 over 9.31. So now if we just invert those, inverse tangent of the numbers, 8.4 over 9.31, that will give us our angle here. All right, so if we plug that in, inverse tangent of 8.4 divided by 9.31 tells us the angle was 42.1 degrees. All right, and there's our launch angle, 42.1 degrees. Okay, that's actually kind of a hard problem. I went through that kind of quickly. We'll take more time to go over it in class and to go over everything you need. I will also, for this, I will have the work solutions posted as an extensive version of the work solutions if you need to follow my work. This one is super fast little slide. I just wanted to show you this one fact. The fastest or the farthest that you can ever throw something or shoot something is at a 45-degree angle. That's the farthest it will ever go. If I shoot something at 30 degrees above the ground and then something else at 60 degrees above the ground, guess what? Follow those lines. They end in the same place. So complementary angles always end in the same place. 70 and 15 end there. 30 and 60 end there. This is 45, and well, what would be complementary to 45 is 45. So those both end there. 45 is the farthest away that we can shoot something, but 30 and 16 end up in the same place. 15 and 75, they end up in the same place. Really, you don't need to remember the complementary part, but you do need to remember this, that 45 degrees will give you the maximum distance for something. All right, I know this was kind of a longer video, so thanks for sticking with me. I will go ahead and stop sharing now. I'll see you in class. Please, please, please let me know if you have any questions. Come prepared to class with what questions you have, and rewatch any parts as needed for you. All right.